In this video, we're going to complete the confidence intervals practice lab. The problem: a high school administrator is concerned that some of the incoming freshmen are not prepared for high school math classes. Now, there are two different middle schools that feed into the high school, North Hills and South Hills. She suspects that the students from North Hills are more prepared than the students from South Hills. She collects data from standardized math achievement tests taken by students at the end of 8th grade. The test is scored on a scale of 1 to 10. Scores from 1 to 4 are below proficient, scores from 5 to 7 are proficient, and scores from 8 to 10 are advanced. Below are a sample of scores from 10 students at South Hills Middle School. So these are data from students at South Hills Middle School. These are 10 students, 2, 4, 5, 1, 3, 5, 6, 2, 2, 10. The goal of this analysis is to determine the average math proficiency of South Hills students by calculating the mean and a 95% confidence estimation, as well as estimates based on a robust estimation of the mean. Let's jump in. So the first thing we're going to do is calculate the 95% confidence interval. In order to do that, we first have to calculate the mean of the sample. Now, we've done this before. This is a common statistical procedure. We add up all of the values and divide by the number of values. So this is the equation for the mean. This symbol right here, sigma, is the symbol for summing or addition. X refers to each individual value, so we're going to add up all the individual values. Those are these right here. We'll add them up, and we'll divide by n, which is the number of observations. So we have 10 observations. So we're going to add them all up, divide by, in this case, 10, and that will give us our mean. So first we have to add up all of these values. To do that, I'm going to open up the calculator inside of the computer, and we'll go ahead and add those up. So we have 2 plus 4 plus 5 plus 1 plus 3 plus 5 plus 6 plus 2 plus 2 plus 10. Okay, I got these numbers from right up here. All of that comes out to 40. So we're going to go ahead and put 40 in this box right there. There we go. There's 40. And we're going to divide by what? We're going to divide by n. N is the sample size. In this case, we have a sample size of 10. So 40 divided by 10. In that case, that is going to be, of course, 4. All right, so 40 divided by 10 is 4. If you don't believe me, 40 divided by 10, of course, 4. Okay, so the mean of our sample is 4. It says here, interpret the mean. What does this suggest regarding the average South Hill student's math proficiency? So it's easy when you're doing math to get calculate your answer. It's 4, and then move on. But we want to stop and make sense out of it. For one thing, when you calculate, let's say, the mean, you want to make sure that it makes sense, right? So we know that this test is scored on a scale of 1 to 10. Okay, and let's say here for simplicity for this practice lab. Probably would look different in real life. But let's suppose that it was on a scale of 100 to 400. Maybe it's some kind of scaled score, so 100 to 400, and we got a mean of 4. Well, if we know the lowest possible score is 100, there's some kind of problem with our calculation. We've done something wrong, or there's an error somewhere. But in this case, this does make sense. 4 falls between 1 and 10. We take a look at the values here, kind of makes sense. We've got a kind of a wide range here. But what does this mean? Well, this gives us an interpretation of the data. So scores from 1 to 4, right here. So let's see here. So scores from 1 to 4 are below proficient. Scores from 1 to 4 are below proficient. So we have a 4. So this average for this school so far is below proficient. These kids, on average, are not up to speed on their math skills. So we're going to go ahead and write this right down here. Go ahead and we'll put a text box there. So on average, the students at South Hills School had a mean math score of 4.0. I'll say 4.0. The question here is, well, how far do we take the decimal places? Typically I go to 2, but when you have whole numbers like this, we might just put 4 or 4.0. It's going to work out the same. A mean math score of 4 Scores between the values of 1 and 4 are considered below proficient. Therefore, on average, the students at South Hills School, have below proficient. Let's see, how about this? Are not proficient in math. So I like to word it using common language, not using a lot of technical language here, so that it just makes sense. So on average, the students are not proficient in math, just below. Right, so we've made sense out of that score. Now it says, look closely at the data. Is there any reason to suspect this estimate may be biased? Well, that's an interesting question. So biased in statistics has a very precise meaning. When we talk about bias, in this case, a bias mean, it means that you have an unusual value that's very high or very low that's pulling the mean in that direction. Remember, the mean of all the measures of central tendency is the most susceptible to outliers. The mode is the least susceptible, followed by the median, whereas the mean is highly susceptible. If we'd had a score of 4,000 somehow thrown in there, right, the mean is going to go way up as we factor that in. So this is sort of asking us to go back and look at the data and see if anything looks a little bit fishy. So let's go back up and take a look. 2, 4, 5, 1, 3, 5, 5, 6, 2, 2, 10. We have a range all the way from 1 to 10. Let's see, 1, 2, 3, 4, 5, 6. But look, there's no 7, there's no 8, there's no 9. It skips all the way to 10. So if we were to graph this, right, we can actually do that. Let's see here. So if we were to graph these data, let's see here, make kind of a histogram, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? We have, let's see here, there we go. We have 1, let's see how many 2s we have. We have 3 2s, make a little taller of a line there. We've got 3, we've got 4, we have a 5, 2 5s, excuse me. And we have, looks like 1 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have a 10. All right, so it's kind of a sloppy histogram, but just to give you a rough idea, it's not super to scale, but most of our students are scoring over here. Below proficient is 1 through 4, 5, 6 is in the proficient range, and then you have this gap, 7, 8, 9, jumps all the way to 10, advanced. So we have one highly advanced student, we have a bunch of below proficient and a couple of proficient students. So it does look like this high observation here, the 10, is biasing our mean. Maybe otherwise the mean would be maybe closer to 3, but it's being pulled to 4 by this observation. So yes, there does appear to be something a little bit suspicious going on. Let's go ahead and say something about that. So most of the scores fall between the values of 1 and how high did it go before it got to 10? 6, right? 1 and 6. So most students were below proficient or proficient. However, I like to be more precise. Instead of saying most, let's just go ahead and say exactly how many. 9 of the 10 scores, right, so 90% fell between, I'll make that past tense, the values of 1 and 6. So most students were below proficient or proficient. However, one student had a score of 10, which was highly proficient. Compared to the other students, this score was very high, potentially biasing the mean. Okay, so we have a possible issue here. The mean that we calculated for, it might be biased. It may be giving us a higher value, higher estimation than we really should have for these students because of this this potential outlier here on the top. Okay, right? If we were to draw this distribution, it would look something like that. So this is a skewed right distribution, or a positively skewed distribution. The skew refers to the tail, right? So most of the very data are here, observations are here, and there's a tail here to the right. People often would say skewed left because they think this is the skew, but it's over here. So this is a positively skewed or a skewed right distribution with a potential outlier on the high end of the distribution. All right, let's move on. Now we're going to calculate the standard deviation. This is a little bit of work. We've done this before. We're going to use this formula down here. This is the formula for standard deviation. Looks kind of scary if you are not a math person. S stands for standard deviation equals the square root. And we have the numerator and the denominator of this fraction. Here, this is the sigma representing the to sum. So what this means is you take each observation, each of the 10, you subtract the mean, right? And you square it. What that's going to do is give you all positive values. We're going to add all those up. Then we're going to divide that by n. That's going to be 10, the number of observations, minus 1. So it's going to be 9 down here, right? So here's how this turns into all this. So the original value is going to go here. The mean is going to go here. For each of these, we'll find the difference. Then we'll square that difference and add them all up. So everything in the numerator is going to end up right here. The bottom is easy. It's just 10 minus 1, right? Because the sample size, n means the sample size, which is 10. It's going to be 9. We divide that and find the standard deviations. I'm sorry, the square root, which gives us the standard deviation. So not so scary. Let's go ahead and do that. We need to put the original values into this box down here. We have a 1 followed by a couple of 2. We have 3 2s, right? So 1, 2, 2, 2. We'll go ahead and start inserting these values down here. So we have 1, 2, 2, 2. All right, then we had, let's see here, a 3, a 4, 2 5s, and a 6. So we had a 3, a 4, a 5, a 5, and a 6. And then remember, it jumped all the way to 10. So these are our original values. The mean's going to go here. They're all going to be the same, right? All the means are going to be a 4. So those are going to go in into the next column. There we go. So it's just going to be a bunch of 4s. 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, and spoiler alert, 4. Okay. Now we're going to subtract the mean from the original value, and that's going to go in this column here. Now I worked this out to give us nice round numbers. You can thank me later. We're just going to make the math a little easier. It's just to save time, so I'm pull up the calculator on the screen and slow down the practice. I don't want you to spend your time subtracting decimals. Just focus on the concepts. So 1 minus 4 is negative 3, right? 1 minus 4. I think in an earlier video I didn't include the negatives because we're going to be getting rid of those anyway over here, but I'll include it now just to make it a little bit easier for you. So 2 minus 4, negative 2, and we have that looks like 3 times, so negative 2, negative 2, negative 2. 3 minus 4 is negative 1. 4 minus 4 is 0. 5 minus 4 is 1. We have another one of those. 6 minus 4 is 2. And 10 minus 4 is 6. There we go. So this is the difference between the original value, or the observation, and the mean. And now we're going to square that. So all of these are going to end up being positive over here on the far column. So 3 squared, 3 times 3 is 9. 2 times 2 is 4. We have another 4, another 4. 1 times 1 is 1. 0 times 0 is 0. 1 times 1, 1 times 1. 2 times 2 is 4. And 6 times 6 is 36. So you can see how the further the value is away from the mean, the more it's contributing to the standard deviation. When we get this 10 way away from the mean, we square that, we're contributing quite a bit to the standard deviation. Now we have to add these. That's what this sigma means, to sum up all of this information and put it in this box right here. So I'm going to go ahead and use the calculator for that one. I'm not that good at math. 9 plus 4 plus 4 plus 4 plus 1 plus 1 plus 1 plus 4 plus 36 gives us 64. So 64 is going to go right down here in this box. 64. Looking good. Okie dokie. Moving right along. So we're going to go ahead and continue to work out this equation. So the numerator, all of this information here, that's what we did up above, works out to 64. The denominator is n minus 1, and again the sample size, which is 10. We have 10 scores. Minus 1 is 9. So we have 64 divided by 9. Right, so we have a fraction, the numerator divided by the denominator. 64 divided by 9 gives us 7.11. Well, we finally got those decimals we were trying to avoid. I'm going to go right under here, 7.11. Now we're going to take the square root of that. right? So 7.11, we're going to find the square root, which is 2.6. I'm going to go to the hundreds place, 2.67. So that's going to round to that right here, 2.67. So the standard deviation of the, I'm going to write that a little bit neater here. 2, there we go, that's a better 2.67. The standard deviation is 2.67. So now we have the mean, which is 4. The standard deviation is 2.67. We're going to use this information as we calculate the standard error in the next section. All right, so moving right along here. So the standard error is the next thing that we need to calculate. So the standard error of this set of observations is going to be the standard deviation subtracted by the square root, divided by the square root of the sample size. So the standard deviation, well, we just calculated that, is 2.67. The sample size is 10. Oh, make a better line. There we go. Sample size is 10 over here. 2.67. Just working this out in steps. Hopefully it makes it easier for you to follow what I'm doing. What is the square root of 10? I'll definitely use the calculator for that one. It is 3.16. So that's going to go down here, 3.16. When this is on the numerator, this means to divide this by the denominator. So 2.67 divided by 3.16 gives us 0.84. I'm going to round to the hundreds place because this is a less than 5 on the thousandth place. It'll be 0.84. So the standard error is 0.84. Excellent. All right, now let's move on. The last step in calculating a 95% confidence interval is to calculate the lower and upper boundaries, right? An interval has to have boundaries somewhere between these two values. Based on the central limit theorem, we know that 95% of sample estimates will fall between 1.96 standard errors below and above the mean of the sampling distribution. Therefore, we will multiply the standard error by 1.96 and subtract it and add it to the estimate mean to calculate the lower and upper boundaries respectively. Okay, let's take a look at the equation for this. So basically we're trying to get a boundary where 95% of the estimates are going to fall between these two numbers. So it's given us more confidence about what the true mean is of these students at South Hills, I guess it's middle school, their math scores. So let's take a look here. So the formula is the mean. This is for the lower boundary is the mean minus 1.96 times the standard error. So let's go ahead and fill in some of this information. So we remember that the mean is 4.0, which is the same as 4, or 4.00. So it's going to be 4 minus 1.96 times, what was that standard error? 0.84, right up here. So let's get that in here, 0.84. So it's going to be 4. This is going to carry down here, 4.0 minus, make sure you know that that is not 40. There's a decimal place right there. Make that a little bit clearer. 4.0 minus 1.96 times 0.84. Pull out my handy dandy calculator. 1.96 times 0.84. I'm going to round this to 0.65. All right, so it's going to be 1.65. 1.65. There we go. So 4 minus 1.65 is going to give us 2.35. So that is the lower boundary, 2.35, the lower boundary of our confidence interval, our 95% confidence interval. What about the upper boundary? Okay, so here, actually, you know what we're going to do? There's a typo right here. We're actually going to be adding. So we're going to take the mean. We're going to add, right, the 1.96 times the standard error, because we need not the same value, right? It's going to be higher. So the mean is still the same, right? It's going to be 4.0. There we go. That's 1.96 times the standard error, 0.84. All right, so we have 4 again, minus, and this is still going to be the same, 1.96 times 0.84, 1.65. And now we're going to actually be adding this. There we go, adding this. We'll go ahead and correct that in the template you'll be using. 4.1.65 gives us 5.65. There we go, 5.65. Excellent. So our confidence interval is going to be, let's see, we give our reader the mean. So the mean is 4.0, and the 95% confidence interval, and they use brackets to represent that, is 2.35, and on the high end, 5.65. There we go. Interpret these findings. What does this tell us about the average math proficiency of the students? So what do we know about the true mean of the students? So the observed mean is 4, but our 95% confidence interval is 2.35 to 5.65. So if the mean is somewhere between 2.35 and 5.65, what does that mean? Let's take a look back at the beginning. It tells us that scores from 1 to 4 are below proficient. So the mean could be as low as 2, which is definitely in the below proficient range, and as high as, I think it was 5.65, which is just on the low end of the, low to mid end of the proficient range. So the true score is somewhere between below proficient and proficient. So we have a little more leeway there. Let's take a look and say something about that. So the 95% confidence interval ranges from 2.35, which is below proficient, to 5.65, which is proficient. The mean of this school falls within this range. Okay, so they're somewhere between below proficient and proficient, and so that now we have a little bit less information, right? If we want to be more confident, right, 95% confident, now we're like, well, maybe they're in the below proficient, maybe they're in the proficient, whereas before, when we just looked at the mean by itself, it showed them being in the below proficient range, So let's see what happens when we use robust estimations. Let's go ahead and go down, because remember, we were concerned about potential bias. Right, we had a potential outlier right up here. We were drawing this out, so we had most of the scores over here. There was a gap, and then the 10 was way over on the side. And we know that the mean is heavily influenced by outliers, so it's going to pull the mean up. But this also has an effect not just on the mean, but on the confidence interval via the standard deviation. Right, so you see what happens when we put that 10 into our equation. We ended up adding 36, right? We looked at the sum of the squares. 36. Think about how much lower this would have been without this observation. So the higher the sum of squares, right? By the time we work this out, the higher the standard deviation, and since that's in the numerator, the higher the standard error. So that widens the confidence interval. It widens the confidence interval. If we had had a smaller amount of variability, right, without this outlier, it would have narrowed the confidence interval. So we might have a lower mean and a narrower confidence interval, which might give us a different estimate. Here we're saying, oh, they're somewhere between below proficient and proficient. But what happens if we use a robust estimate? So let's go ahead and try that. Okay, so before conducting our analysis, we're going to generate a robust estimate of the mean by creating a 10% trimmed mean, and then calculate the 95% confidence interval for the robust estimate. So robust means that we're basically accounting for outliers, right? There's something that violates the rules. When you have a statistical analysis, you have certain assumptions, and when those assumptions are violated, something's quirky about the data, we use some kind of a robust technique which accounts for that. So that's what we're going to do here. One way of calculating a robust estimate of the mean is by using a 10% trimmed mean. So how does that work? The first step is to remove the top and bottom 10% of scores to stabilize the mean and the confidence interval. Now, because there are 10 scores in our data set, this means we're going to remove the highest and lowest score. So first we have to write the 10 scores in order, and you'll get a sense for what this looks like visually. All right, so what were our scores? I'm going to go up to our table again. I don't quite have them memorized. There we go. So we had 1, we had 3 2s, 4 5, 3 4, a couple 5s. So 1 2 2 2. Let's go ahead and start writing these out. Pardon my scrolling. Okay, so we had 1 2 2 2 3 4, and I believe it went 5. There were 2 5s. 6, 1 2 3 4 5 6 7 8 9, and then there was that 10, right? It skipped up to 10. To make sure that's right. It's 1 2 2 2 3 4. Yep, that's it. Okay, so we're going to get rid of the 10% highest values, 10% lowest values. There's 10 of them. That makes the math easy. 10% of 10 is 1. So we're going to cross out the lowest and the highest. That means we're going to get rid of the lowest. Goodbye 1. Get rid of the highest. Goodbye 10. In order to calculate a confidence interval, we must first calculate the mean of the sample by adding the scores and dividing by the samples. And you may say, wait a minute, we already calculated the mean. It's 4, right? But things have changed. We've gotten rid of the lowest score and the highest score. We know that 10 had a lot of influence. So let's see how that affects the mean. We'll go ahead and pull our calculator back up. So 2 plus 2 plus 2 plus 3 plus 4 plus 5 plus 5 plus 6 gives us 29. So the new sum of the observations is 29. That's going to go right here. Divided by n. Now the sample size has changed. We've deleted the lowest and highest values, so it's gone from 10 to 8. So now we have 29 divided by 8. Our new mean is 3.63. I'm going to round to the hundreds place. 3.63. 3.63. There we go. Now we're going to interpret that mean, right? Again, we don't want to just get the value and move on. Let's think about it. Let's make sure it makes sense. What does this suggest regarding the average South Hill student's math proficiency? How does this estimate differ from the original estimate? Okay, so let's take a look here. Based on the explanation from above, scores between 1 and 4 are below proficient. So that hasn't changed. It was 4, now it's 3 and some change. Still below proficient. And how does it vary from the original? So let's go ahead and address that. Okay. The robust estimate of the mean is 3.63. This indicates that the average South Hills student is below proficient in math, right? Just like before. How does this different? This mean is somewhat lower than the original estimate of 4.0. I'm going to put 2 zeros just to be consistent with the number of decimal places. All right, so it went from 4 to 3.6. Now, can you explain why the robust estimate is different from the original? Right? Why did it go down, and which one is a better representation? Let's think about that for a minute. All right, there we go. So it went, let's say, first of all, it went down. So the robust estimate is lower than the original estimate, right? Why? This occurred because, well, why did this occur? We took out the lowest and highest values. 1 was kind of packed in with the other observations, but 10 was way out there. Remember, we drew this a little bit ago. A little shoddy histogram here. So we took out the 1, but we also took out the 10. This 10 had a lot of influence over the mean. So what we're going to say here is that, there we go. Let's see. Okay, because we removed the highest and lowest observations. The highest observation, 10, was a potential outlier which had, that's how you spell it, outlier, which had a lot of influence over the mean. Now, which is a better representation? One's lower than the other one. Well, I would argue that the robust estimate is actually a better representation because that kid we took out, the 10, was a bit of an outlier. He's not a typical South Hills student. Okay, so the robust estimate is a better representation of the data because the high scoring student, who is not typical of the South Hill School, has been removed. There we go. So we have we've gotten rid of the outlier. We've done it in a fair way, took out the bottom and the highest observation, and now we have a slightly lower estimate, still interpreted the same, right? Below proficient. That's what we knew before. That's what we know now. But let's see how this affects the confidence interval. So next we will calculate a 95% confidence interval for the robust estimate of the mean. First, we have to calculate the standard deviation and standard error. So here we go. We've got this table again. Purposely included this several times. I want you to get comfortable with this. I know a lot of students are kind of scared of complex equations or not math people. And so you take a look at something like this and it seems really scary. So by doing this over and over again, explaining it again and again, I'm not trying to bore you or hopefully annoy you, but make it seem less scary and a little bit more intuitive. So the formula for the standard deviation is we add up the different, we take the values, subtract the mean, we square that, right? And then we sum the squares, and then we take that, divide it by the sample size minus 1, take the square root. All right, we'll begin here. So the original value we need to include here. So let's see here, we'll get this fresh in my mind. 222, 34, 556. Let's see if I can remember that. So now there's only 8 rows. 2, 2, 2, 3, 4, 5, 5, and 6. 2, 2, 2, 3, 4, 5, 5, 6. Looks good. Now the mean has changed. It's no longer 4. The new mean is 3.63. So that's going to go in all of these cells. 3.63. Here we go. 3.63. Over and over again. Our subtraction is going to get a little bit more complicated now. We'll have to pull out our calculator. 3.63. Now as before, we're going to subtract each value from the mean. Or, the mean from each value. There we go. So it's going to be 2 minus 3.63, which will give us negative 1.63. It's going to go right here. Negative 1.63. This is going to be the same. It's the same. We have the observation 2 occurs 3 times. Negative 1.63. 3 of those. What about 3? 3 minus 3.63 will give us negative 0.63. All right. What about 4 minus 3.63 gives us 0.37, a positive 0.37, and then 5 minus will give us a 1.37, another one of those, 1.37, and then 2.37. So 6 minus 3.63, right? 2.37. Looks good. Now we need to square these over here in the final column. So we'll use a calculator for that as well. So 1.63 times 1.63 gives us 2.66, again rounding to the hundreds place. So 2.66, my decimal in there, there's 3 of those, 2.66 and 2.66. And then we've got, we're going to square 0.63, which will be 0.40, again rounding, right there. And then we have 0.37 squared, which gives us 0.14, 0.14, and 1.37 times 1.37, 1.88, 1.88, another one of those, 1.88, and then finally 2.37 times 2.37, 5.62. Rounding, 5.62. So look at the difference, right? Take a look at our sum of squares. They range from 2.66 to 5.62. There's none in here that are really high. Compare this to before. When we calculated the standard deviation last time, we had we ranged from 9 all the way to 36. So the sum of squares the squares, the difference squared, were much, much higher, right? We ended up with a sum of squares of 64. Let's see what happens now, right? We're going to add these up. So 2.66 plus 2.66 plus 2.66 plus 0.4 plus 0.14 plus 1.88 plus 1.88 plus 5.62 gives us 17.9. So our sum of squares, 17.9. I'll add a 0 there for consistency. So look how much that has changed. Our sum of squares went from 64 to 17.9. It's gone down quite a bit. Why did that happen? Well, we remove these more extreme observations that are further from the mean, which lowered the difference, right? Which lowered the difference squared. So our sum of squares is much smaller than it was before. Let's see how this factors into the rest of the equation. So this is in the numerator, 17.90. Right, so all this turns into 17.90. 2 minus 1, right? So now n is 8, because there's 8 observations. We got rid of 2. So 8 minus 1 is 7. So 17.9 divided by 7 is 2.56, rounding. There we go. And then we're going to take the square root of that. 2.56 square root 1.6. There we go. So 1.6. I'm going to go ahead and add the 0 again for consistency. So our standard deviation of the robust estimate of the mean is 1.60 compared to, what was it up here? 2.6. So it dropped by quite a large proportion. Okay. So what is that going to do to the standard error? Because the standard error is a function of the standard deviation, which is in the numerator. So the smaller the numerator, right, the smaller the value. So let's see what happens here. So standard error equals a standard deviation divided by the square root of the sample size. Standard deviation is 1.60. The sample size is 8. Okay, so it's going to be 1.60 divided by the square root of 8, which is 2.83. That'll go right here, 2.83. And now we'll use the calculator again. 1.6 divided by 2.83 gives us 0.57, rounded. 0.57. Okay, so the standard error last time with the original data was, where did it go? 0.84. Now it has been reduced to 0.57. It's gone down quite a bit. Now, what is this going to do to the confidence interval? Remember that the confidence interval is a function of the standard error. The larger the standard error, the larger the confidence interval. Right? That means we're less confident because the mean could be somewhere within a wider range. It's somewhere between here and here, and the here and here are further apart. Okay, so let's go ahead and take a look at how that works out. The lower bounds of the confidence interval. So it's the mean minus 1.96. 1.96, because it's a 95% confidence interval. If we were to be more confident, let's say 99% or 98%, this value would be higher. If we wanted to be less confident, let's say 90%, this value would be lower. So the more confident we want to be, the wider that standard error is going to, I'm sorry, the confidence interval is going to be. And the larger the standard deviation and hence standard error, the again, also the larger the confidence interval. So ideally, we like to have a small confidence interval, but not because we want to be less confident, but because we want to have a smaller standard error, so we have a good idea about what's going on with our sample. So our mean is not 4 anymore. What was our mean? Let's go ahead and take a look up here. Our mean was 3.63. Okay, so that's going to go in this first box. So 3.63. Now we're going to, let's see, we need the standard error, which was 0.57. That's going to go right here. And 3.63 remains the same. Now we're going to multiply 1.96 times 0.57, which gives us 1.12, rounding, 1.12. And now we need to subtract 3.63 minus 1.12, which gives us 2.51. 2.51. So this is going to be the lower boundary of our confidence interval. Now what about the upper boundary? Now again here, these should be pluses. We'll go ahead and make sure we get that fixed for your template. There we go. So the mean is going to be, of course, the same, 3.63 with for our robust estimate. 3.63 is going to be there. Okay, and then 1.96 times the standard error. The standard error is the same, 0.57. This will be the same as well, 1.12. So the only difference here is we're subtracting, and then here we're adding. So this is the lower bound, this is the upper bound. 3.63 plus 1.12, 4.75. 4.75. So the 95% confidence interval, right? So the mean, 3.63. The lower bound, 2.51. Upper bound, 4.75. So let's take a look. How does the interval for the trim mean differ from the original confidence interval? So here it's between 2.5 and 4.75. Last time it was between 2 and 2.3 and 5.65. So the bottom has stayed about the same. It's gone up a little bit, but the top has dropped quite a bit. So the bottom coming up a little bit makes sense because we dropped off the 1. That's no longer in our data set that was pulling down the mean, but it still hasn't changed too much. But the top has come down, and the two reasons for that, right? The mean itself dropped because we got rid of the 10 that was in the data set, that outlier. But this whole interval is more narrow because we have a smaller standard error, right? So before the confidence interval, let's see, what was the range of that? Let's see here. We didn't talk about that. So 5.65 minus 2.35, 3.3 was the range of our confidence interval, 3.3. But now, 4.75 minus 2.51, it's 2.24. So because we got rid of that big observation, right, we got rid of the outlier, it reduced our standard deviation, which reduced our standard error, which narrowed our confidence interval. So now we can be more confident. We're still 95% confident, but now we have a narrower range to work with because we're using that robust estimate. Okay. So let's go ahead, and it says, how would you explain this? Okay, we'll put that in writing. And based on these analyses, what can we say about the average math proficiency? So we're going to interpret that too, right? The interpretation is going to change a little bit. So let's see here. So the confidence interval for the trimmed mean is narrower than the original confidence interval. This occurred because we eliminated the extreme value. Ooh, extreme, there we go. Because we eliminated the extreme value, which was increasing the size of the standard deviation, standard error, and confidence interval. Okay. So we got rid of that, narrowed that confidence interval. So how would you explain that change? We talked about that. Now, interpretation. Okay. So before, when we interpreted this confidence interval, we said there's somewhere between, let's see, not right there. Let's see here. Where did it go? We're interpreting this. Right, which is below proficient to proficient. So they were somewhere between below proficient or proficient. The average of the school definitely wasn't advanced, but they were somewhere between these two groupings. Now let's look at the cutoffs again. 1 to 4 are below proficient, and it's not until 5 that you switch to proficient. So let's go back down here. Our confidence interval goes between 2.5 and 4.75. So that whole range of that confidence interval falls in the below proficient range. Okay, so this is a significant change. Let's see. In the original analysis, the confidence interval spanned both the below proficient, let's put that in quotes, below proficient and proficient categories. So categories. So our estimate was less precise. However, let's see here, the trimmed confidence interval, or let's say the robust confidence interval, fell completely within the below proficient range, meaning that on average, South Hill students are not proficient in math. Okay, so when we talk about this confidence interval, we say, okay, well, we have 10 scores. We have limited data here, so how well is this representing the true mean of this group? How good is our guess? So our guess gets better as we use this trim mean. In the original analysis, we say, oh, okay, it's going to be somewhere in the below proficient range. But now that we've used this more robust estimate, and we have this narrow confidence interval, we're saying, yeah, on average, these kids are below proficient, right? You might have some advanced kids kind of thrown in here and there, but this is the best representation of the students at this school. Hopefully this was helpful to you and made sense, and that you'll be able to move forward with confidence in your work in confidence intervals. Thank you.